Save 8% off your order at TruTechTools.com by using the Shop Talk discount code. Hello, everybody, and welcome back to HVAC Shop Talk. I'm your host, Zack Psioda. We'll go ahead and run through our commenters real quick because we have a brand new member. What's up? Michael Bemko there, Frylock 87 HVAC. Awesome. He's our first member since we reinstated the membership policy, which is really, really cool. Speaking of that, there's two different ways you can support the show. Actually, there's a whole bunch of different ways you can support the show. You can give the stream a like. As far as the podcast, which every show we do that's live gets made into a podcast. Usually it lags about 5-7 days behind the actual live stream. If you listen to the podcast and you like it, leaving us a review, 5 stars with maybe some writing underneath it, because those always make the biggest difference if you write something about what you like about the show. So you can do that. You can give a like to this stream. You can go ahead and become a member if you want to, or you can support us on Subscribestar, which is it's similar to the membership, except it's kind of, I use it for a blanket for everything I do, like the podcast, the Men with Issues show that we do on Friday nights. All that is kind of supported by Subscribestar. So I want to say hello to our buddy Tool Pros, Brent, our buddy who just received his monetization curse. Right, Brent? We have Will Justice. What's happening, Will? Sam Holsey. So I listen to your guys' podcast. Hey, that's what I'm talking about. But he's probably talking to Tool Pros. I'm guessing he wasn't talking to me, but hopefully he listens to this too. Clint Glasgow, who's a good supporter of this show. And we have Tony McKay, our buddy from down at Kalos. Tony McKay, young man, very nice guy. So I think that's everybody. We have Old Handy Luke as well and Randy Lass. Just real quick, we usually have a couple podcasts every week. We have a couple live streams every week. This week we had Nathan Orr on Tuesday night, which will be a podcast that is released next Monday. And then tonight we have Jamie Kitchen from Danfoss, and that'll be a podcast released probably next Wednesday. I think we're going to do Monday, Wednesday on podcasts and Tuesday, Thursday on the live streams as much as possible. Also, in the description of this show, you'll see a link to sign up for text notifications. So whenever we go live, I will actually text you. I do it about 5 minutes before the show, and I'll actually send you a message that says we have 5 minutes and a link to watch the show to make it really, really easy. Like Randy Laz is already saying, this is going to be a good one. All right. A lot of pressure on us to deliver here. Hopefully we can do that. I think we can. And Bob Reddington says, hey, Zach, Bob, I got to tell you, you won a prize last time. I never got an email from you. So make sure you email me with your address. If you guys can see right here, that is a prize that we gave away last time. It's going to be going out tomorrow with, every show we're doing something. We're giving away a little something because we have all this promotional swag. So we need to get rid of it anyway. So I think this week we have a hat right there, hat and a shirt. And if you already have a hat or a shirt from us, then we can substitute it with something else. But we're going to give away one of those at the end of the show. I think we'll do the hat and the shirt. So we have large, extra large, and 2XL on those. So I'm glad to say that Sam says he listens to both podcasts. That's good. Listen to as many podcasts as possible. There's some good ones out there, guys. Hopefully you do listen to ours, but there's guys like Gary McCready. That's HVAC Know-It-All. There's HVAC School, HVAC Uncensored, and those are the main ones that I always think of. And of course, Brent has Tool Pros, which is in the chat, but that is a general tools podcast, which is really good because typically if you like HVAC, then you probably like tools too, which I do. I love tools. And just so Brent knows this, because I know Brent loves Ryobi products and he can't help himself. It is better than Milwaukee. I agree, Brent. It's wonderful. Hopefully they'll create their own pack out called the Ryobout or something like that. Something that's very similar. But I was using their 40-volt chainsaw and cutting up some cedar trees today. So it was nice. Very nice. I love doing stuff like that. Love tools. So listen to Brent if you want to learn more about various tools and watch his YouTube channel. He needs the views now that he's monetized. He has some sort of monetization curse. He got monetized and the views just tanked. Sorry, Brent. I'm just kidding with you, man. Of course, there's more links in the description, Facebook, Instagram, all that stuff. We're not going to waste any more time talking about that stuff. We're going to get on with the show here. I'm going to have a quick commercial here from our buddies at Navac talking about their new battery-powered flaring tool. And just keep in mind that, like at the beginning of this show, if you get something like that from TrueTechTools.com, use our Shop Talk discount code. That's the way that you can tell them that you heard it from us, which makes a big old difference. So let's watch that spot, and then we'll be right back with Jamie Kitchen. We are back. Welcome to the show, Jamie.
Thank you. I was just drooling over that flaring tool. Did you see, like, it even has like the diameter checker on it and the roundness trueness checker on it? I mean, that's impressive.
It is. It's very nice. I filmed that little spot down at my shop, and I've used it a couple times, or actually more than a couple times. But it's really, really nice, and the flares it makes are very pretty. So it's a nice tool. We're gonna give it away too one day, but I'm holding on to it for a while. So for testing purposes.
Yeah, that's it. Oh yeah.
Yeah. Whatever I need to say to make it all right with everybody, but I'm keeping it for a while. And but Jamie, how's it going, man? First time on the show here.
Yeah, absolutely. Things are going well. I mean, seriously, it's definitely a different time. It's an interesting time. I'm usually an outside sales guy, outside engineer. I pretend to be a sales guy. I'm actually a technical person. But since March of last year, I haven't been on a plane. In fact, the last time I actually ate in a restaurant was probably mid-March last year, by the way.
Really?
For my son's birthday. Yeah, no, Canada here, I mean, Ontario, they shut everything down pretty tight. They open up a little bit in the summertime, but to be honest with you, we just spent more time outside than really inside. So, I mean, because it was just so nice to be out. But, yeah, it's still pretty tight. It's still pretty, I can't go see customers, so everything's online.
I can't believe that's so different than here. Here, we're semi-open. I mean, we go out to restaurants all the time, although we have protocols that we have to follow once we're in the restaurants.
Sure, yeah.
But everyone's open down here, except for, there's some things like, I guess, bars have restrictions and places like that for whatever reason. But different world up in Canada. That's interesting. You haven't been on a plane since last March. And I'm guessing you were on planes constantly before that.
Well, yeah, I could do that in my car. Southern Ontario is like this huge, straight line run between Quebec and Windsor. It's, 400 or 500 miles kind of thing. I had to convert the miles in my head. But yeah, so I mean, you can spend a whole lot of windshield time, but at the same time, you want to fly out to Vancouver or Calgary. And then I also spend a fair bit of time in the States too, back and forth. So yeah, to go from one extreme to the other, it was a lot to get used to for sure. But I'm starting to miss it again. I was so glad not to have to do it. Now I'm like, man, I could really handle going somewhere right about now.
Yeah, it's got like cabin fever, especially if you haven't been out that long. I can't even imagine that.
Yeah.
Wow.
Yeah. Now restaurants, they are kind of open, but they're like, as you say, like 1/3 opening or whatever.
Right.
But I don't know, man. Just haven't got around to it.
Wow. Well, let's talk a little bit about, because this is your first time on the show, so I'm kind of introducing you to my audience. So there's dozens of us, by the way. So just so you know, there's dozens of people that are going to see this.
Oh, cool. Awesome. A couple dozen, man. That's almost like 500 or something, isn't it? Yeah.
Well, 1.5 dozen. Okay, well, it's the same. 18, 1.5 dozen. Nah,
That's awesome.
I'm just kidding. Uh, now, talk about like how you entered this sector of the trade. I know it said whenever I was reading about you that you've been in the trade for 32 years.
Mhm.
How did you spend that time, just as like a quick overview of your life up to this point in the trade?
Well, I was actually pretty fortunate. Um, there a couple of dead ends happened when I was getting into it, but instead of jumping out, I just took whatever detour came around, and it's actually taken me, into more interesting things. Originally in the mid 1980s, okay, I'm going back to how old I am. I was born in 1966, so when I was 19 years old, they were promoting this new program, 3-year program at a college for solar engineering. So I thought, oh, great, solar engineering, can't go wrong. So first semester in, government pulls the funding on it, all right? So it's like, ooh, okay, now what am I going to do? So they said, oh, they got this building environmental systems course, indoor environmental, right? You should go into that because it's, very similar. So I did, and I really haven't looked back. So after 3 years of college, I worked weekends, helping with centrifugal teardowns and things like that. Got my hands working around big iron, and actually worked back and forth at the school for a while. In fact, you mentioned Gary McCready. He was a student there when I was working at the college for a while.
Wow. Okay.
And so, yeah. So, we've known each other forever and ever. And it does happen. You run into people at the school. A lot of them have done well. But then I got in with Danfoss and as a, application engineer. And I've had multiple jobs since then. So I did a lot of field service work, a lot of field application engineering, troubleshooting, things like that. It's been a good ride. I mean, I've been with them since 1999. So that's how long I've been in this. Yeah.
22 years with
Yeah.
Danfoss. Now, is your familiarity with the larger stuff in HVAC, the larger, like you mentioned, we were talking earlier, or when I was reading about you earlier about supermarket stuff, you're just talking about centrifugal chillers. I'm assuming that's what you're talking about. So is that your experience in your career? It's all been the big stuff?
Originally it was. And then when you take that jump from that into commercial refrigeration, now keep in mind, when I was doing the supermarket stuff, it was all mechanical. There was no electronics. There was, like the CTR, and that was just coming out. As far as the building controls, the Metasys system had just been introduced back then, like 1989, 90. So a lot of that was just coming in, and a lot of it, was a bit of a disaster because there was no understanding of it. There was poor adaptations, things like that. So when I went into commercial refrigeration, when I got in with Danfoss and commercial air conditioning, it was a lot to get used to because everything was small, but at the same time, it was more tightly controlled. Do you see what I'm saying? Like, have you ever seen the metering device on a centrifugal compressor, like a centrifugal chiller at the time? It looks like your floor drain. It's about this big, and it's got about 40 holes in it. And I'm not making it up. I'm like, this is the meter device. Well, that was anticlimactic, right? This thing weighs like, 12,000 pounds altogether. And this is your meter device, right? So commercial refrigeration, believe it or not, to me at that time was harder to understand than these large centrifugal systems that were just basically mechanically controlled. So plus you don't have as much room to move around in them either.
So you like the mechanical side more than like the intricate control side?
Yeah. I understand the control side. I work with it and things like that, but I really enjoy the actual refrigeration side and the air side of things for sure.
That's interesting. I've always been a residential person, which to me puts me at the bottom of the totem pole. So when you guys talk about this other stuff like rack systems and things, it's always been like a theoretical for me because I had to imagine based on what I've read or what I've heard because I've never worked on it. So it's always, whenever I think when people get in that situation, I was like, wow, those are really cool. The people who work on that's really cool stuff.
There's a lot of different things. I mean, if you look at your evaporator and your condenser, right, and you're changing heat back and forth. In a supermarket system, you have multiple places where heat's going to and multiple, places where heat's going to and places where heat's coming from. But at the same time, you can also share that to other places. Like you got heat reclaim, you've got subcoolers, you got all these other things. They're all based on the same, laws of thermodynamics. But to me, I have ADHD. So when I start reading about programming, my eyes just glaze over and, I just nod off somewhere. So, I've taken multiple controls classes at Danfoss for the 2 series and 3 series and 8 series controllers for supermarkets and buildings and stuff like that. And I enjoy it. The problem is I forget it practically a day after I've learned it all, right? You know what I mean? It's just this way my brain works. But with mechanical systems, I have this ability in my head to picture air flows and heat flows, on both sides of the evaporator and both sides of the condenser. I know exactly what should be happening. And I can tell when something's not right because that energy balance is just off in my head. So that's why I've kind of focused on the refrigerant air side, because it just seems to become, it's something that's, what's the word, tangible to me. Whereas the control side, it doesn't seem tangible to me. You know what I mean? So it's like trying to remember a name.
I can totally understand that. I mean, I kind of feel the same way about it. I don't know a ton about controls because in residential, our controls, it's limited. We don't have to know a whole lot. It's not
going to be like that for very long, I can tell you that. So, I mean, because with the way things, energy are going and with variable speed drives and communications, it all depends on how the manufacturers decide to bring this stuff to market. But I'm telling you, man, I've seen some really nice residential multi-zone systems before. And it's a work of art watching these guys put that stuff in. Like some of the nice ductwork and that I've seen, man, it's like art, metal and art almost. Right. So
well, I can understand that more now. I understand it. When you start talking about ductwork and stuff. Okay, I'm with you now.
Yeah,
I can understand now, because what we were going to talk about here tonight is a lot about what you were just mentioning, the air, how it behaves across an evaporator. You mentioned a condenser too, which we could talk about that as well. Mm-hmm. And so let's start. I want to start with my most, I guess, comfortable area, which will be comfort cooling, mm-hmm. and then we can get out of the comfort zone, which I like to do anyway. But
okay.
What conditions, if we can pinpoint in a general way, what conditions are we looking for in comfort cooling? I know that can be broad and it can be up to people's interpretation.
But it is. I mean, if you look at AHR or ASHRAE, I mean, it's, 75 degrees Fahrenheit, 50% RH, mm-hmm. in that range there, the vast majority of people are going to not complain. Let's put it that way, barring any outside air streams and things like that. But as you move into things like long-term care home and schools or places where there's very low activity, basically things like that, you're going to have to look at a slightly higher dry bulb temperature, so 78, along those lines, because, believe it or not, some of these people are vulnerable to hypothermia, even sitting in a, room where you would be comfortable, because they just don't have the body mass. They don't have that, the capability to metabolism to maintain that. Whereas on the other side, you've got people who are active and things like that, where they can get away with a lower temperature. So, but generally speaking, 72, 75, 45, 55% RH, people aren't going to complain too much. To me, it all depends on what you're actually doing, because I'll feel hot most of the time anyway. So, I mean, it's one of those things, but that's what you want to aim for. Now, in the wintertime up here, 50% RH in your house would be a bit of a disaster, because you would have condensate on your windows. So even with, multi-glazed windows, multiple pane, I mean, you have to look at what is the dew point. Okay, what is the temperature that water is going to start coming out of the air, right? Just like, condensing on your glass. Well, if you get your humidity too high, it's going to start to condense on the windows. And the colder it is outside, right, the lower the internal humidity, that is going to start to condense on the windows. And of course, you don't want that, because that starts to cause mold and all kinds of, wood rot problems with the windows, you name mm-hmm. it. So generally speaking, a lot of times 30%, maybe even pushing 35, that may be even pushing it, in some places where it's, minus 10, minus 15 Fahrenheit outside. Right. So the thing I can say about humidity is it is just as important in comfort cooling than dry bulb temperature, like, your normal temperature that you read on the wall with your thermostat. If you, in the wintertime, if you lower your RH, relative humidity, by 10%, right, You know, in the summertime, yeah, if you lower your RH by 10%, you can crank your dry bulb up a couple of degrees, 2 or 3 degrees, and you'll still have the same comfort because your body can cool itself easier in low humidity, right?
Mm-hmm.
No, think of the opposite. Think of being outside in the summertime. You're in North Carolina. I remember living in Baltimore for 2 years. All right, and it'd be 92 degrees outside, and I swear to God, it was like 99.9% humidity or something. That's the way it felt out, anyways, outside.
Yeah.
Well,
Yes.
you'd go into a mall. They still had those then, right? And you would just about, pass away from hypothermia. You were cold and miserable. And then 15 minutes later, you totally forgot about it and you felt normal again, right? Because your body had acclimatized to that new condition. So it's working like heck. Why? Outside? Because of the humidity. The temperature, sure. But I've been down in Arizona where it's 95 degrees outside, a light breeze is blowing, and I almost froze to death when I got out of the pool. Why? Because it was so dry outside, the moisture it evaporated off me like alcohol. You know what I mean? It just chilled you right down to the bone. So that humidity has a huge impact on how you feel, almost more than the dry bulb does, really.
So that would be the reason why in those climates that you talk about getting out of the pool when you were cold, sort of like an evaporative cooling. That's why they use things like swamp coolers.
Swamp coolers, yeah. Yeah. Okay. No, that makes absolute sense. If you have low humidity, in fact, to be honest with you, we do the exact same thing when we humidify. When you run a humidifier, you probably don't worry about this too much down there, but up here, you run a humidifier in your furnace because, again, moisture's energy, right? It's dry outside because of the low temperature compared to inside. So you have to add energy in the form of moisture. Well, when the air comes off of your hot air furnace and it's 130, 140 degrees and it passes over that humidifier, the total energy in the air is exactly the same when it leaves. The difference is you've traded dry bulb, sensible energy, for wet bulb, latent energy. So your dry bulb temperature drops, right? And your moisture content goes up. Well, that's the exact same way that a swamp cooler works, right? You're trading one form of energy for another. So by going from a very low humidity to a slightly higher humidity or moderate humidity, you can drop the dry bulb temperature substantially and bring it back into that comfort area again. And that's whether you humidify or dehumidify, it's called constant wet bulb, constant enthalpy processes.
That's pretty interesting. I never thought of it like that. So there's somewhat like a balance between the two. Yeah. Interesting. So, okay. Well, that's a lot of information right there. So let me ask you a couple questions based on what you just said. So we're talking about the comfort zone, and you said that you could see relative humidities of 30 to 35% where you're at.
In the wintertime, yes.
Where do you reach a point where you're having nosebleeds and discomfort because of the dryness? Do you guys have that? Because I have that when it gets dry in my house.
Oh, absolutely. I mean, 100%. I mean, we, I can tell just by how I feel in the morning when I get up. I'm plugged up. I'm sneezing. Every now and then you'll blow your nose, and as you say, there's dried blood in it. Right, which is again not good for health because, that nasal mucous membrane up there being wet is one of your major defenses against, pathogens getting up in there because it traps it. And then, as you say, you sneeze or whatever happens, and that gets rid of it. That's why when you get on a plane, what's the temperature on a plane at 40,000 feet? It's minus 60 degrees outside. It doesn't really matter if it's Celsius or Fahrenheit. It's still cold as heck, right? Well, the RH on a plane is 3%. Okay, so you're sitting there beside people who have who knows what, right? And it's 3% RH on there. It is like a pathogen love fest on this plane because you've lost all of your natural defenses most of the time. That's why you usually feel like total crap when you get off a plane, right? It's not because of lack of oxygen or whatever half the time. It's just because you've dried out everything in your body that's not supposed to be dried out pretty much.
You make complete sense because I had literally just read that same thing about the atmosphere in the book that I'm reading. That's good.
Yeah.
Talking about atmospheric pressure and the temperature at different parts of the atmosphere. That's it. 3%. I can't even imagine being exposed at 3% for a long period of time because I'm so uncomfortable at 25 or 30%. It's just, I feel like there's like my mouth is dry, my nose is dry. It's just horrible. But
that's amazing.
We don't have that problem here. Like you're saying, even in the wintertime, it doesn't get that cold outside. We don't have those dry conditions inside. Now it can from time to time, but it's not very bad because
your challenging months for dehumidification and cooling has to be probably late April and like late October, maybe November, when you get that swing month when it's 70 degrees outside, 65 degrees. Do you have like, I mean, did you get a wet? You wouldn't get a wet season, I guess, but
not really. But yeah, the month you described, like today, was even that way. We were in the mid 70s outside. There's a little bit of humidity, and I actually enjoyed it more outside than I did inside the house because the AC didn't run. The humidity was building up in the house. I think it was at like 65%, which is not uncommon here, especially in my house. Which is
65% humidity in the summertime is not bad, really, to be honest with you, because I mean you got to do a lot of work to get it lower than that.
Yeah, well, we try real
sounds like
hard
a segue. Here. Sorry, yeah, that was good.
Yeah, that's good. Okay, I should recognize that. That's exactly right, because we're going to talk about how the air behaves across a cooling evaporator, and one of the big things is dehumidification. You already mentioned sensible and latent heat. Let's sort of go back and break that down a little bit. Okay. So just to keep it really basic, sensible heat. A lot of people are familiar, like you said, the number on the thermostat. How do you really convey the concept of latent heat?
Latent heat, really, for most people, they see it all the time, but they just don't realize it. Latent heat is something that causes a phase change. Okay, so you wonder, man, why does this glass of water heat up so fast in the summertime, right? You think, oh, because it's warm outside. Well, that's partially true. There is a larger temperature difference, dry bulb, between what you're drinking here and in the air. But the main culprit is that literally the air coming into contact with that glass can only cool down so much before it hits a wall. And that wall is when moisture starts to condense out. So now instead of taking one form of heat out of the air, you're taking two. So instead of dropping, 1 degree dry bulb is equal to so much energy, it's 1 degree dry bulb plus all of this latent heat baggage that you also got to take out of the air before you can actually drop that 1 degree. And then you got to take out even more latent heat for you to drop another degree. So that latent heat is what really causes two things. One, for your drink to stay much colder for longer when you put ice in it. Why? Because the latent heat of the ice melting into your drink is a lot more energy dense than just, the water itself, right? So it's like a reservoir of cold almost. I hate to say it that, but that's really what it is, right? So the second part is you've got that working against that, you've got that condensation occurring on the outside of the glass that is just pouring heat into that liquid as it's moisture is condensing. Remember the first time I went to Alabama to visit some friends down there. I had some nursing friends that we were friends in college. I went down to see these girls. I'm like, well, why are you giving me my beer with this, shirt on it, this napkin around it, right? Well, once it had sat on the table for about 30 seconds, I knew why. There was a napkin wrapped around it because the moisture was just pouring off of this thing on a hot summer night in Alabama out on the patio. Beautiful weather. I saw cockroaches the size of, practically size of house cats running around down there. I've never seen that before. But I also had this beer that was sweating like there was no tomorrow, so interesting. I have no idea if I answered the question, but
that's the same thing. Yes, it does. It gives us a segue into talking about the HVAC part of that. So we have a cooling coil. We have air going across this coil. So that air is going to reach its dew point because of the cold coil, and it's going to there'll be condensation. So that's the same sort of thing you're talking about with the can.
Yes, absolutely. And the best latent heat example is when you sweat. That evaporation of sweat is exactly your the blood in your body does the same job as the oil in your engine, right? Oil provides lubrication, but it also removes heat from the core of the engine and brings it out to an area where the glycol or the antifreeze can pick that heat up and put it into the radiator. You can't run glycol in the middle of your engine, right? Where the oil is, because it wouldn't work. So the oil, basically when you sweat and you're overheated, right? What happens is the blood comes under the skin, right? Your sweat pores open up. And that evaporation, that cooling effect, right? That is latent heat, right? When that moisture evaporates, right, and turns to a vapor, it actually pulls heat from the surrounding skin. That's why you feel cold when you put alcohol on your skin, right? for that very reason. That's latent heat, 100% latent heat.
So if we have a condition like where I live, let's say
Mm-hmm.
it's a lot of humidity
Mm-hmm.
and we're trying to cool the air, we're going to have a lot of that condensation and we're going to have to remove a lot of that heat before we get into the sensible. Is that why our sensible splits get smaller and smaller?
It's going to be sensible. And then when you hit that dew point and moisture starts to condense, in order for the air to continue to drop sensibly, you have to start scavenging or pulling out more and more and more latent heat. So the expectation is if you took, inside air at 78 degrees and it was 50% RH in one situation and 75 RH in the other situation, with the higher humidity, 75% moisture going in, you would expect your dry bulb temperature leaving the coil, your mixed air condition, to be much warmer than it would be with the lower humidity at 50%. Why? Because you don't have that moisture, you don't have that latent heat break, holding back the temperature drop across the coil, because you don't have that same level of latent heat coming out. It's mostly sensible heat coming out. So on a drier day, your air temperature through the coil is going to drop like a stone because you don't have that, latent heat to worry about. Whereas on a swampy day, when, the humidity is very high, you're going to hit that dew point early at a relatively high temperature, and it ain't going to drop very far because you're going to have all this moisture you got to pull out of the air. And because you're operating at a higher temperature and because your coil's at a higher temperature, right, that's going to improve the performance of the system. That's why you'll see the COP of systems go up and their capacity go up when you have times of high latent heat, high humidity on the loads.
Oh, that's interesting.
Yes. Yeah, you pull out any, documentation for a package unit, rooftop unit, whatever it is, and you look at the performance curves or you look at the ratings of it at different conditions, you'll notice that on high humidity, all else being the same, it's kicking butt.
All right, so let me ask a series of stupid questions that you can answer. So if I have a machine, I'm kind of working through this in my mind right now, so forgive me. I have a machine, and let's say it doesn't have any latent load on it. It's going to cap out beneath the total capacity because there's no latent load on it?
Well, here's what's going to happen. I mean, hypothetically, we're talking about here anyways. Yeah, if you have a very dry load, your evaporator temperature is going to drop. Depending on what the system was designed for. If the system was designed to operate with a higher load, a higher latent load, your coil size and everything else, then you would expect your evaporator temperature to be lower. So, because let's say you have an adaptive expansion device, TXVs. All right. The TXV doesn't really give a crap what the load is, whether it's latent or sensible. It's just going to react to the amount of superheat leaving the evaporator. So if you have a relatively dry air going across the coil at a given CFM that you use regardless, you really have less heat going across that evaporator because you're missing this big chunk of latent heat. So with less load, what's your TXV do? Throttle's closed, right? Or throttle's more closed. Well, now you're injecting less refrigerant into the evaporator. Well, that refrigerant has to go somewhere. Well, how do you reduce the pumping capacity of a fixed speed compressor? Well, you drop the evaporating temperature, right? You lower the density of the vapor going into the compressor so that every time that piston strokes down and up again, it's drawing less mass in. So if you pull the capacity chart out for a compressor, you look at, let's say refrigeration, for example, minus 10 and plus 10. Well, why does this compressor have 70% more capacity at plus 10 compared to minus 10? Well, because the gas going into it is 70% more dense, right? Because compressors don't pump BTUs, they pump pounds per minute of refrigerant, right? That absorbs heat. So when your evaporator throttle's closed or your evaporator ices up or, your fan forgets to turn on, for whatever reason, and your load drops, TXV throttle's closed, and we all know what happens to your evaporating temperature. It drops like a stone, right? So an interesting, caveat to that would be if you happen to tailor your cooling system for latent heat load and you're running, 320 CFM a ton or something through it, and you're running a 42 degree evaporator temperature like you see down in humid areas, and you get some freak day where it's dry outside, well, yeah, good luck getting the ice off your coil, right? Because whatever moisture's still on there is going to freeze on the surface. Oh yeah, I got a defrost cycle on my AC system, man. It's just defrost clock or something, right? Yeah,
And you said you didn't like controls.
yeah. No, I do like that part of it, but it's just kind of funny because I like the energy side of it. So really, if you look at it as an energy flow going through the system, it's easier to picture from that standpoint. And with a fixed orifice type situation like a piston, you're still going to see that drop in evaporator temperature. It's just not going to be as extreme as you would see it in a TXV, because you still got a relatively large mass flow going into the evaporator, because the piston, how much it puts into the evaporator is based on your pressure difference, right? And that doesn't really change that much. In fact, if your pressure goes down in the evaporator, your pressure differential actually goes up. So you actually put more refrigerant in the evaporator, which has got no heat to evaporate it. So that's why I like TXVs.
It makes sense, and that's where you get a situation where you have zero superheat, because your TXV, there's no load, or not TXV, but your piston, there's no load on it.
Yeah, in fact, you have some people say, I got negative superheat, because if your gas is coming out of saturation, or your vapor is coming out, or liquid's coming out of saturation, it's going to be colder than when it went in, because you got a pressure drop through your coil, right? And saturation temperature is tied to pressure, right? So you get a 2 or 3 psi pressure drop through your coil, it's going to come out 3 or 4 degrees colder than when it went in. So it's
does
no
that
problem
mean
keeping the compressor cool.
Yeah, that's true. So if you have a, let's say, theoretical negative superheat, is negative superheat the same thing as saying it's subcooled?
Yes, it is. Yeah.
So it's still subcooled coming out of the evaporator.
Well, it's not subcooled per se. It is at a lower saturation temperature. You're still going to have vapor in it. You're going to have liquid there. And if you have a mixture of both, right, then it's at saturation. And as soon as you have that both there, as soon as you change the pressure, the temperature of it changes. So you're literally going to have flashing going through your evaporator based on pressure drop at saturation, rather than just heat transfer, right? Which you'd have normally anyways, but you don't have that superheating region.
Right. So would you say semi-flooded would be the description?
Semi-flooded, yeah, absolutely, with really good oil return. Yeah.
Yeah, that's funny. Well, it's very interesting. The most interesting part that I heard there, it's something I haven't really thought about, was the amount of refrigerant flowing through the compressor, thinking of it as pounds of refrigerant, because I've never thought of it that way, which kind of gives, and I'm trying to work through it here in real time, which is very difficult because I'm trying to kind of catch up and imagine that. So you lose, and this is a recap for my benefit and whoever else is remedial that's in the chat. So you have a low temperature, a low load, your capacity is going to go down because it's not pumping the same amount of refrigerant. It's not as dense.
Yep. And because your compression ratio also goes up a little bit, your COP is going to drop as well. Your current will go down because your compressor's not working as hard, but you're not going to realize all of those savings, because unfortunately your compression ratio, the pressure difference between the evaporator and your condenser, is still going to be greater. Your condensing temperature is going to drop a little bit because you're not rejecting as much heat, but unfortunately you're not going to realize all those savings, so your compression ratio actually does increase. In fact, that's really the big way we burn out compressors, is because loss of charge, your evaporator temperature goes into the toilet, but your superheat goes through the roof because you haven't got rid of your load. You just got rid of all your refrigerant to absorb that load, right? So you come out of the evaporator with 10 million degrees of superheat or something like that. You go into your compressor. Well, the scrolls, like anything else, they're 95, 99%, suction gas cooled. You lose that cooling effect, right? You're going over the motor. You're picking up all that extra heat. You're highly superheated anyways. And now you compress that vapor. Your discharge temperature goes up. And if you look at your scroll, the middle of the scroll, right in here, is your discharge area. Well, if you flip that mobile scroll over, what's sitting on the opposite side of your discharge? The bearing, the main bearing that you have with your oil in there. So when your discharge gets, 260 degrees and your oil has zero viscosity underneath it, you lose all your lubricity, right? So that's why that main bearing, you take apart any scroll that's burned out, right? Apart from the chunks that's inside of it, you look at that main bearing and it's completely fried underneath. That's the first thing that's going to go, is your lubrication under there. So, Everything else that adds to that is just gravy, crappy voltage, phase imbalance, whatever it happens to be, poor condenser airflow because, somebody put a hedge around it or something, those all add to it. But the end result is just the fact that your compression ratio was high and you didn't have enough gas coming back to keep the compressor cool. That's rule number one. That's why it died. So
would you say a standard compression ratio somewhere between 2 and 3 to 1?
Yeah, something along those lines. Something? That's about right, because you add atmospheric pressure 14.5 psi to it or whatever, and then divide them. Yeah, it's probably about right off the top of my head. I used to remember stuff like that, but maybe the age or something. I don't know.
It starts to go. My brain purges stuff that I don't use after 5 days.
Oh yeah. Well, that's part. That was engineering. Engineering and technical schools like that. You learn thermodynamics, right? You write the test, you walk out the door, you go to the pub, you meet your girlfriend, whatever. Yeah, it's gone, man.
It doesn't help that she's yelling at you because of something you did, and now
you don't know why.
What's the first law of thermodynamics? I don't know. Let's just go home.
Yeah. If something gets hot, something else gets cold. That's how it works. Yeah.
It goes from one to the other. I don't remember which way. But okay, let's say, because I'm imagining when you're talking about this, I imagine that low charge, and I've seen the compression ratios on a low charge on the systems that I've worked in, comfort cooling, R22, and then R410A, and they can be like 10 to 1. I mean, it can be quite high. So what is the cutoff in your mind where you go into the danger zone? Anywhere over 3 to 1?
I don't really have an answer to that, to be honest with you. Again, it depends on a lot of things. It depends on, scrolls are pretty survivable as long as they're getting cool. So if your compression ratio increases, as long as the gas coming back is cool enough to keep the compressor cool, you're fine. Look at a refrigeration scroll. Refrigeration scrolls, even without liquid injection, they work at refrigeration compression ratios, and they have no problem. Now, the wrap geometry, the spiral of the scroll is slightly different, but the fact is that, the refrigerant those scrolls will work at, 10 degrees Fahrenheit or 40 degrees Fahrenheit, right? As long as they have the motor, they'll work fine. You look at, if I look at the application envelope, okay, people wonder what the heck's an application envelope. Well, that's what you set your high pressure control to and your low pressure control, in case you're wondering. Just throwing that out there. But your application envelope is what conditions can this compressor operate in. It's got a minimum evaporator temperature, a maximum evaporator temperature, and a minimum and maximum scroll condensing temperature and pressure. Most air conditioning scrolls, at least the ones that we see, they'll operate down to 5 degrees Fahrenheit, no problem, right? But you got to limit your condensing temperature, and you have to limit your superheat. So if you're running 12 degrees of superheat at a scroll compressor at 10 degrees Fahrenheit, it'll be happy, right? As long as you maintain that condensing temperature where it's supposed to be, it has no problem. Because really, as long as you're cooling that motor and it's not overloaded, it doesn't really care. It's just going to keep operating, right? So that's your main concern. That's why I can't really give you a compression ratio. Because if your superheat is really, really high, your limiting compression ratio is going to be very small compared to, low superheat. So
you're saying also that when you get into lower temperature refrigeration, your compression ratios are going to grow naturally.
Yes. And your tolerance to superheat goes down. So, we use this really contradictory and weird term. I should say but it's called saturated suction temperature. Okay. So, saturated suction superheat. Okay. Well, hold on a second here. How can you have saturated and superheat at the same time? That's just dumb. Well, what they're saying is, if you take the actual saturated temperature at the suction line of your compressor, it's going to be lower than at the evaporator, like we talked about earlier, because you have that pressure drop. So if you calculate your superheat there, it's going to be higher than it was when it left the evaporator, because it picks up additional superheat, but also because the pressure goes down as well, right? So when you take that consideration, at air conditioning situations, you want at least 30 degrees of superheat at your suction inlet at your compressor. And that's a minimum with air conditioning, right? Whereas in low temp refrigeration, let's say you're running an ice cream freezer and you've got your evaporator run minus 20, right? Well, 12 degrees of superheat at the compressor is just fine, right? Because again, the amount of superheat that you can tolerate goes down with lower temperatures because you got to keep that compressor cool. It's harder. Your window of, this wide window that you can operate at higher evaporator temperatures gets narrower and narrower and narrower as your suction temperature goes down. Because again, you have to cool that compressor.
Now for HVAC, for high temperature, how much superheat is the assumption? If you have 30 degrees at the compressor, what are you assuming is happening at the evaporator in general?
This takes us back to humidity. Because remember you talked about that, what happens when you have dry air as opposed to, moist air hitting that coil. Well, you are going to see that on your superheat. Because again, load is load, right? Once you start, get below dew point temperature, it really doesn't matter what type of load it is. You're still going to boil off refrigerant to get rid of it. So if you look at our expansion valves for air conditioning, if you buy one in aftermarket, they come with about a 7-degree static superheat. In other words, that means the valve won't even open until you have 7 degrees of superheat. And that's standard, right? Whereas an OEM valve, one that comes, installed at a York or Trane or Carrier unit, they can have as low as 1.5, 2 degrees of superheat or 3 degrees of superheat. Same for ice machines, right? Very, very low static superheat. But at the same time, why is that? Because you always operate your AC system with a load, right? What is the temperature difference between a walk-in box and a unit cooler? Was it 12 degrees? 13 degrees maybe?
I have to go with if you say so.
Yeah. What's the temperature difference between your AC coil at 45 degrees and your house, right? At 75 degrees. It's a 30-degree spread, right? So because of that huge spread, and you're throwing latent load in there, you have an opportunity for massive amounts of superheat. And this is what you're going to see. Even with a properly sized TXV, it is not uncommon to see 16 degrees of superheat leaving your evaporator under high latent load. And that's with a TXV that starts to open at 2 or 3 degrees. All right. So again, you have this very large window of superheat. But again, it all depends on how they size the components, your airflow, your moisture, and everything else. So generally we're sizing, A coils bigger these days so that we can run them with higher temperatures. Unfortunately, that negatively affects the moisture removal, but it also allows you to operate with, lower superheat and lower temperature spread between the evaporator and the air. So,
but then we swoop in and lower the CFM so we can all be comfortable.
Yeah. Same thing. Yeah.
So are we canceling out the good effect that they've set up at the factory?
Well, that's a good question because I often wondered that because I remember when Sierra 13 came out, as the bottom standard, it was like 2007 or something like that. It was a great day for TXV manufacturers because most, AC manufacturers went from pistons to TXV. Before that, TXVs were used on higher efficiency systems. Now TXVs are used on just about everything, right? So millions of TXVs were sold that year. I forgot what I was going to say now. Oh yeah, the evaporators actually got bigger because it's an easy way to save energy. You make your condenser a bit bigger, you make your evaporator a bit bigger, right? And everything works better. But at the same time, I'm thinking, okay, so you're going to save, a few bucks a month or more on your electricity bill.
Right.
But what if you're ignoring that whole, moisture removal, humidity treatment thing? I mean, okay, I know it's extreme, but if you got a mold issue you have to treat in your house, that's not cheap, right? That can get very expensive. And so are you really saving any money? I have a water heater at home that I rent, believe it or not. I've replaced that venter motor on it 3 times. It didn't cost me anything because it's rented. But okay, how much money-wise in natural gas did I save by having a high-efficiency water heater compared to the cost I would have had to have somebody come in and change that venter motor multiple times?
Oh,
right?
Yeah.
I often wonder about that. But anyway, that's a side story.
I also wonder about that same thing. That's like a whole different show.
Yeah, I know.
Efficiency versus logic.
Yeah.
Well, we had the same thing back in like the early 2000s and late 1990s where we were in 12 SEER. Yeah. Because they would take the 10 SEER equipment, and to me, it looked like they would just oversize the evaporators. Like you had a 2-ton split, they'd have a 2.5-ton evaporator, try to push it and get that extra bit of efficiency out of it. Well, 2 things happened. First, we had pistons back then, by and large, and they'd leave the original piston in, and it would be improperly sized because the evaporator would come with a large piston, and the superheat would be 0 or 2 on every single one of these back at the compressor. Or
you'd have
we'd
great
no
humidification because your average coil temperature would be low. But
yeah, it was relatively flooded most of the time. But
yeah,
you put the right one in there.
Accumulator in this thing, man. Yeah.
That's exactly right. Good thing most of these systems had suction line accumulators.
Are you serious? And AC systems like that, really? Eh?
There were heat pumps. All these were heat pumps because they were for in the wintertime they needed that extra bit of protection.
I almost fell over there, man. Well, man, who didn't read that blueprint, man? Because you'd never see that today, man. As far as I know.
No, I don't see it in any of the ACs. It's just the heat pumps because of the wintertime operation.
Sure, no, that makes sense. Yeah, when reversing it.
But it was a mistake that was across the board, and kind of speaks to your other subject about people have the best laid intentions when they design and make things, and then when they get out into the field, they're totally screwed up, both by the implementation and just by like the piston being left in there. Like change out the piston with the proper piston. It never happens.
I've had service calls like that, man, where the guy installed a TXV, converting the system over from a piston to a TXV. Mm-hmm. Didn't take that piston out of there, man. Sitting in that distributor, right? Thread that TXV on there. Whatever he did, 2 metering devices in series don't work better than one, man. But it's like, that's an expensive mistake to make, man.
I've got a great counter story for that because Rheem had a bunch of air handlers and package units that would have a TXV and then another larger piston, larger than normal piston that sat in the distributor. So there would be 2 in series, but the Rheem would be much larger. It'd have like where you'd have like, let's say a 3-ton took a 72 piston. Well, this would be like a 100 or whatever the equivalent.
Really? Like, what was it, acting like a spacer or something? Like what?
I never got an explanation on what it was, whether it fed refrigerant in a special way into that distributor or why they put a little throttling down.
It was like a turning vane almost for the freaking refrigerator.
That was my assumption. But the problem was whenever people would change the TXV, they would say, "Oh, this is the wrong piston," and they would have the TXV, and then the piston would be, and they move it down to a 72, and of course,
you got a pressure drop.
Yeah, there was quite a pressure drop, and we had high compression ratio on that one.
Yeah,
but it's funny because they were the only ones like that. They were strange. They're the only ones I ever saw that were like that.
Yeah, I never heard that before. That's interesting.
I think they're gone now. That was a series that was probably 15 to 20 years ago, I think.
Oh, okay.
So everybody's safe now.
Yeah. Well, yeah.
From the idiosyncrasies of Rheem.
Mm-hmm. Yeah, they bought Russell out, I think, actually. And I'm thinking more on the refrigeration side now. And they got some really nice equipment. But
that's where your mindset's at. I think of heat pumps. You think of refrigeration. Just that's our go-to thing. I always think of heat pumps because that's all I ever worked on.
I worked on a lot of air-to-air heat pumps. I remember the old Coleman units, man, that we used to see running around. Mm-hmm. You guys have Coleman? That's an American brand, right? Coleman.
Coleman. The ones that I worked on, Coleman was the same as York. It was the exact same piece of equipment. They were all brown rectangles.
Yes.
Little squatty units a lot of the time. Yeah, absolutely. Plenty of them.
I used to see those things. Remember one time, and this is a disaster, a whole bunch of electric furnaces. Electric furnace, no big deal, right? Back when, nuclear energy was going to be a big thing or something. I guess they figured electricity was going to be free or something. I don't know.
Oh, yeah.
But they put all these darn A coils on top of these furnaces rather than at the bottom of them, right?
Oh, sure. Yeah. Wow.
And I often wondered, is that not really stupid? Like,
to draw it through and then go into the furnace after the cooling process.
Yeah.
Yeah. There was the same thing, except we would have it depending on different package unit configurations where they put the coil, whether it was a slab or whatever was inside the package unit, as opposed to where the heat exchanger was. Because some would be after the heat exchanger, which makes sense. Some would be before. And there was condensation built up in the summertime inside the heat exchanger.
Yeah.
So you would have water in the heat exchanger.
Hey, man.
So, yeah.
It's a potable water. I don't know.
Maybe we
can upsell that somehow. I don't know.
But it would drain out eventually through the holes in the heat exchanger.
Yeah, well, that's good. That kind of concerns you too. But anyways, yeah.
Safety first. Yeah.
Yeah.
I've noticed that one a few times. But I've worked on those electric furnaces too. They put those A coils on top of them, and
I found out the hard way. They only break them on one side too. Eh?
Yeah, well,
if you touch that thing and you're now aground, congratulations, man. You completed the circuit. I didn't realize that till I did that. I got a piece of sheet metal up my elbow because my hand shot back so fast, man. That hurt.
That's pretty funny. Yeah, they're in manufactured housing All these
Uh-huh.
like we call them trailers. I don't know if you call them trailers up there, but
I
single
like
wide, double wide.
manufactured housing. It sounds cool, actually.
Manufactured housing makes it sound better than it is because there we go in there, and some of these things were old. I mean, now I live in a modular home right now. I mean, it's nice, but back in the day, you'd have either modulars, and I did have one 20 years ago as well, or trailers, and they'd have these electric furnaces and A coils in every single one of them. Two things guaranteed: they would be rusted up, bad. Second one would be they'd probably be out of refrigerant anyway, so it didn't matter.
Well, it sounds like the economizers on some of the rooftop units, right? It's like I think it worked for about 6 minutes after they installed the unit, right, and then it stopped. But the economizers always seem to rust up on those things too. The rod that came out of them. It's like, what do you guys use, mild untreated steel on these things or something?
Yeah,
But
or they were just unplugged or something. I mean, I've seen a lot of the Molex plugs just laying dangling there. It's like, well, that's why that doesn't work. Okay. Got it.
Yeah, no, we could. Yeah, there's hours of stories we could go through on some of this stuff. But anyways, humidity, right? We're speaking of economizers and things like that. When you're dealing with let me ask you a question now. You got these tight houses now, right? People are building these, very tight houses where you control the air going in and out of them, right? What are the main technologies that you see now for controlling humidity? Now, like in other words, you're bringing untreated air in the summertime, right? And you're exhausting treated air out. Now, obviously, you might as well just throw money out the window if you're not going to, do something about that. So how, like these big energy wheels they have, how do they deal with the moisture side of it? Do they have like some kind of desiccant? Is it like a giant filter dryer or something inside that thing? Like, how do they work?
That's interesting. I was talking to Bill Spone, who built a house high efficiency. And I know that some of these devices, these heat exchangers that are crossing in between the outside air coming in and inside air heading out, they'll actually have like a small system built into it, refrigeration system built into it.
Oh, really? So you're actually, hey, that's actually.
I don't think they're all like that. I think some of them are just exchanging heat through whatever media is in the middle of that thing. There's no refrigeration system, but the one he was going to put in, I know had a little refrigeration system built into it.
Yeah, interesting.
It's uncommon though. I don't think most of them are like that. I think most of them are just the cores that are exchanging heat.
Yeah, like a heat wheel or something like that goes around. That was just kind of interesting. No, I thought, okay, sensible heat. Yeah, sure. I mean, I get it, right? But there's got to be something that's going to act like a filter dryer, like a desiccant that's going to, pick up moisture in a high moisture zone. I don't know, right? And I don't know.
Well, I know there's two different versions. There's a version that's just sensible. I know that. And then I don't know a ton about it. I know there's one that removes some kind of latent heat because it has a drain.
Well, yeah, it has to. I mean, how again, you got so much moisture outside, that'd be a huge expense, man.
Yeah. And they might have dedicated dehumidification as well. I don't have that here, but I mean, it might be a good idea. So you have that extra control over it anyway.
Yeah. Speaking of dedicated dehumidification, you're probably going to start to see more of that even on the residential side, just because the technology now is getting to the point where it's easier and easier to do. The biggest challenge we have right now is the fact that the thing that's reading the air on the wall, your thermostat, misses the majority of the energy in the air, which is latent heat. It only senses dry bulb. So, I mean, you can have 50% more energy in the air and your thermostat doesn't even realize that. And that has a huge impact on how you feel, as we talked about earlier. So I think, if you look at a lot of the larger equipment manufacturing like Daikin and things like that, they have this ability to go into multi-cooling modes. So you have, economy modes where you do mostly sensible cooling. It's like, I don't know if you remember like boiler reset and stuff like that, when you used to deal with if you had a warmer day outside, you could raise your temperatures and things like that. Same kind of idea. If you have dry air outside, then you can, raise your evaporator temperature. You can do all kinds of things to save energy. Whereas if you have a day when you have a lot of moisture, right, then you can run that system in such a way with reduced airflow, lower evaporator temperatures, maintaining your, compressor capacity, things like that to focus on moisture removal, right? And one of the interesting things is that little portable dehumidifier that you have in your basement is actually a wonderful little contraption, because literally some of these big units now are taking that, little residential portable dehumidifier, flipping it on its side, and actually installing that as a module or modular part of some of these air treatment things. So you literally have a section of coil of evaporator and things like that, where you actually cool the air down below what it's supposed to be, and then reheat it back up again with your condenser, which is how those dehumidifiers work, right? Because, little warmer, drier air is just perfect. And so, when I asked you about those swing months where you live, we get that a lot up here too, where you don't have that huge sensible demand. So what are you going to do when it's 75 degrees outside, it's pouring rain, and your house is damp, right? Because it's 100% humidity outside, that moisture is coming in. What are your options for getting rid of that moisture? Well, if you run your air conditioner, the only way to do it, even if you lower your CFM, is to cool your house down to 66 degrees or something like that to get rid of the moisture. Of course, nobody's happy then. So if you could have this little dedicated dehumidification system built into these, units that could focus on, not only cooling the air down and removing moisture, but actually reheating it back up again, I think that would be a really great idea. And I've started to see a lot of ideas coming along those lines. So I'm not a betting man, but if I was going to put $20 down, I think you're going to see a much larger focus on dehumidification, right? Even during periods of time when you don't have high sensible load, that's going to be a focus for a lot of these systems going forward. And just like everything else, anti-lock brakes. What was the first vehicle that anti-lock brakes? It was a Concorde, right? Now you get them on your, $10,000 Kia or whatever you're buying now, right? So, hopefully that technology starts to become mainstream, but it's high time we have an option available to control the moisture in your house rather than just your day-to-day AC system, even if it is properly installed and charged. So that's kind of a parting shot on that.
Well, first of all, I don't know how you knew I love Kia, but thank you.
Yeah, no worries.
They're fantastic.
Kia, man.
You got to put them together yourself, but that's fine.
Yeah, some assembly required. That's
a joke I heard on Friends a long time ago. I love my Kia, but I put it together
man.
myself.
Friends, that brings back me. How old are you, man?
41.
Oh, okay. All right. Because
you were thinking 30. You were thinking 30.
Yeah, that's it, man. I was wondering if somebody had to come and pick you up after this was over and drive you home.
My mom. Yeah, my mom's going to be here shortly. That's right.
My kid's I saw this police officer the other day. This is how I know I'm getting old. I'm looking at this kid. I'll call him a kid because I swear to God, he was like 18 or 19 years old at the most, right? I'm thinking, man, when did I get old, man? This kid looks like he could be my son now, right? Like here he is walking around in his, police uniform, right? It's amazing, man.
That's how I knew. Whenever I would go into the supply house in the later parts of my field career and look around, it's like all these people are younger than me now, except for like one guy. This one guy that's a single man company. He's like 60. But besides that guy, I'm the
he ain't going anywhere, man, until they take, they carry him out of there kind of thing. Right?
That's exactly right. He will quit when he dies. Basically, that's what's gonna happen. He's gonna fall over, and that's the end of his career. That's it.
Yeah.
Man, exactly. But I had a question I was gonna ask you. Now I can't even remember what it was because I was
I don't remember either. In fact, hey, you got it written down somewhere?
Well, I have extra questions I write down the whole time. Here's what it was. It came off of what you just said. All right, this is just a question from me personally, and just thinking about this. Dehumidifiers.
Yeah.
It's basically it's spitting out that warm condenser air on one end. It's taking in air and then lowering the temperature, condensing out some of the water. The water goes out the drain. So talking total heat from one end to the other, is it minus the water, you're losing that much heat? How much difference in total heat is there from one end to the other?
Well, actually, you're leaving with more energy in the air than you entered, because if you look at it, your heat of rejection out of the condenser is more than what you absorb in the evaporator, right? Because you got your heat of compression too as well, right? So,
okay.
I mean, you got your, you talk about heat pumps, okay? The money you pay for is the heat of compression, right? That's the energy that's being used in the compressor. Your free lunch is your net refrigeration effect. That's the heat you absorb out of the air or the water or your neighbor's basement or whatever you happen to be drawing heat out of, right? And that hopefully can be several times the energy that you're paying for in the compressor, right, to run it. So, if you want to compare it to straight electric resistance, right, your electric resistance with 100% efficiency, COP of 1, that's your compressor, right? So if you take your, refrigeration effect, that's what you're doing in the evaporator when you dehumidify, right? And so, because it's moist air, you're probably running your evaporator a little bit cooler than you would normally, right? Because you're focusing on dehumidification, and then you run it through your condenser. So, just to throw some random, I pulled these out of my butt answers. If it goes in there at 73 degrees in your basement or 72 degrees in your basement, it might come out at 78 degrees or something like that, right? With less, less moisture in the air,
right,
a higher sensible temperature. So yeah, the total energy in the air has actually increased a little bit, but that's exactly what you want, because the warmer the air is, the more moisture it can pick up, right? So now, not only have you dropped the moisture in the air, right, but you've also raised its temperature. So now you've got warm air with very low relative humidity coming out of your dehumidifier. And that's going to go out there and scavenge moisture out of your basement and everything else. Because keep in mind, the moisture in the air is a very small part of it, right? Everything in your house absorbs that moisture until it reaches saturation. In other words, the moisture content in the space of your house, which weighs thousands and thousands and thousands of pounds, is the same as the air. So you got to pull that air out of there consistently, pull moisture out of there until you dry all your surroundings. That's why when you first start your dehumidifier up, you can't keep that thing empty. And then after a few days, it's like, man, where's all this moisture coming from? Well, it's coming from your house and your furniture and you and everything else, right? That's really what it is. So it's just like when you go to heat up, if you ever rent a cabin in the wintertime and you go there and you crank the wood stove up, nice and hot, as soon as that fire goes out, what happens to the temperature in your cabin? It goes down, right? Because the walls are all still 40 degrees, right? Same kind of idea.
So as soon as the dehumidifier starts, it creates a delta in humidity level, and it starts moving out of all that furniture, moving out of anything that's stored up that energy into the air, then into the dehumidifier.
Moisture is vapor pressure, right? That's what humidity difference is. And vapor pressure, high pressure, low pressure, you all know which way that's going to go, right? That's why when you have a shower in the wintertime, when it's dry in your house, you think, man, these towels in this bathroom dried in 30 minutes, right? Why? Because that high vapor pressure just took that moisture and shot it all over your house is what it did, right? It is just literally moisture vapor traveling through your house at rapid speed. It really is. It's amazing, right? Whereas in the summertime, your house is wet. It's got the same vapor pressure. Man, these towels are still damp when you go to bed at night, right? Practically, because there's no evaporation, right? So really, the drier the air becomes, the more rapid you're going to pull moisture out of everything. Why? Because it's energy. You're going from a high energy state to a low energy state. It doesn't matter if it's moisture. It's no different than you stepping outside on a 10-degree Fahrenheit day wearing a t-shirt, right? That you're going to give up a ton of heat because you have a lot more heat than the air does. Well, it's the same thing as me getting out of that pool in Arizona. The moisture on me had a much higher vapor pressure than the air did. So that higher pressure energy just caused that moisture to literally explode as vapor off of my body, causing this massive cooling effect, right? And that's really what you're doing, right? I mean, you spilt water there on the sidewalk. It was gone almost instantaneously. It was amazing.
You felt really cool for about 5 minutes.
Yeah, exactly.
Well, I'm going through our list of things here. We actually did cover quite a bit of it. Actually.
Yeah. Oh, wow, that was pure luck, man. I don't know, on my side anyways.
No, I think you're right. I think it was pure luck because the show never contributes any efficiency to getting through the list. So
isn't that amazing how that works? It's like me going into the office once a year. You go in there with all these things you want to get done, and you leave at the end of the day and goes, well, there's 8 hours of my life I'll never get back, right? It's like
I didn't write ERV on any of these things.
What's ERV?
Energy recovery ventilator.
Yeah, okay.
We sort of, that's the device we were referring to earlier. HRV and ERV, and then the thing Bill Spohn has, which is, I don't know what you call it. It's another level. CERV maybe.
Curve RV, yeah. It's like, yeah.
It's a super RV. It's a great RV. But, I mean, we're pretty much at our hour plus some here, and this pretty much ensures we're going to do this again because I had a good time. I think.
Oh, thank you. I did too, man. This is awesome. It really is. I appreciate your time.
It's no problem.
I actually been looking forward to this for a while now.
Well, you can look forward to another time because you're definitely coming back because we didn't get through all this stuff, and I know this is just the top of what we can talk. Yeah, that's the beauty of it. We won't.
Never any end to this, man.
we can talk about all sorts of, and there's more questions on this subject, which maybe we could talk about next time as well. I think that'd be great.
Oh, great. Yeah, absolutely.
We didn't get into like supermarket stuff at all, really, except for just a light dusting there.
I don't know. Why do they always overcool supermarkets so much? Like, really? I mean, I know you're controlling moisture, but you have to make it feel like a November day outside when you're inside of these places in the summertime. I mean,
they do that. That's for sure.
Like, I know you're trying to dehumidify, but we just talked about heat recovery, and like supermarkets were like one of the number ones that started that. So I just never understood that.
I don't know. Like, is that a teaser because you do know, or are you just
no, not really? No, I just
okay.
One of those things that make you go,
by the next show,
Hall show, yeah,
we'll know by next time. Somebody will know. It won't be me. Somebody will know though.
Somebody, yeah, isn't that amazing? Somebody will come up and go, I can tell you exactly why that is, and that's awesome. That you get that information coming to you because of that.
Absolutely. We have a lot of people that watch this show that are way smarter than the host for sure. And I think that's awesome because they'll actually say in the chatting over there. I don't know if you see the chat that's alongside the screen.
No, I don't. I can't.
Because he doesn't have
got my glasses on anyway, so I can't.
Well, it's okay. It's all right. It's not integral that you see the chat, but it's sometimes we can go back and forth with some of the questions. But they know a lot of stuff. They have a lot of suggestions on removing humidity. It's very interesting. Once you go back and watch this later, if you skim, you'll be able to read the chat. It'll be interesting to just kind of review that. So this is the part where we say goodbye, though.
Oh,
because I gotta give away a hat, and we can do this again maybe a month or two from now and pick up where we left off. That sounds good.
That'd be great. Thank you. I appreciate it.
Cool. All right. That sounds really good. Jamie, I appreciate it. Thank you for coming on the show. I had a lot of fun. I learned a lot, actually. Sometimes I talk. Really? You learn nothing. Let's just be honest. You knew all the stuff. You taught stuff. I mean, you didn't learn anything except for where I live, basically, and that I worked on heat pumps, and that's not really scholastic knowledge. That's more,
Well, somebody asked me. I can say I know that, and they'll be impressed. Does that count? I think it does.
I'll take it.
Yeah, we'll look on that.
All right, I will let you go. I appreciate it, and I'll see you when we do this again. Okay.
Thank you. I appreciate it.
Take care, Jamie.
You too. Bye-bye.
Bye. That was Jamie Kitchen, guys. That was a lot of fun. Jamie works at Danfoss. He's worked there for a long time, as you can hear at the beginning of the show there, guys. We're going to have him back probably, I don't know, next month or two. I like to bring people back every couple of months. I think that's a good thing. The guys get used to certain guys talking, and they really enjoy it. And we know a lot of smart guys. In fact, coming up, I'll tell you actually when we come back. I'll tell you after our break here. Let's see. What are we going to do? Do a little bit of EWC here. We'll come back, and I'll tell you about what's coming up. And we'll give away a hat and a shirt here. All right, guys. Be right back. The best forced air zoning controls in the HVAC industry come from EWC Controls. This includes the Workhorse BM Plus 3000 zone panel, 3 zones, multiple dip switches so you can customize the controls to your particular system install. Another workhorse of the system is the URD and ND dampers. These power open, power closed dampers are both reliable and long lasting. So for the entire life of your system, you won't be replacing your zoning components. And lastly, the innovative SBD2 static pressure bypass with the wireless NFC interface take this whole thing to a new level of precision and reliability, because you can set your system right there at your fingertips to the particular static pressure you need. No more guesswork, no more barometric arms. Go to EWC Controls Incorporated. You can find them online to learn more, and look for them in your local supply house. All righty. So coming up next week, I know for sure we're going to have our buddy Jason Objute return to the show. So that is for sure. I am trying, and he's agreed to come on, but I don't know if it's going to happen next week or not. Dave Shanklin, which is our buddy NorCal Refrigeration on YouTube, is supposed to return. We're going to have, of course, our buddy Dave Richardson, who's probably been on the show more than anybody else. He's going to come back for a couple parts segment about an email he received from one of you guys. I don't remember who it was, but he's going to come back, and we're going to talk about that. It's a couple segments there that we're going to do on that. We have a hat and shirt to give away here in just a second. I was getting Nightbot ready. Let's see if he hasn't picked up anybody yet. I don't know what the deal is with this Nightbot. Sometimes. I don't know. So as always, you can contact me. Let me put it up on the screen here by emailing hvacshoptalk@gmail.com. And if you have somebody that you think would be great for the show, feel free to send it to me. I mean, we have a big list of guys. Jenry Garcia is going to be coming on the show in the next few weeks. He has his gear. We had to do a test run with the gear and then have him on. And I can't think of anybody else. I know we're going to have people come back. We have our buddy Steve Demansky. He can come back. We have Bimco. I think I'm going to invite Bimco on the show. There he is. He's here, and he's a member. You know, with that membership, you buy yourself access to this show. That's what I'm saying. Okay. But guys, email me anything you need, questions about the show, questions about people on the show. If you want to contact them, I know we didn't give out Jamie's information tonight, but if you need to contact him for anything, I can be like a go-between for that. Jim Bergman, he's going to come back on the show. He hasn't been on the show in probably about a year. So it's time for Jim to come back. We're going to talk about, I think we're going to talk about the book because he sent me this book and I've been reading it. You guys know that I've been reading this book. And you see, I'm about 1/3 of the way through it. Yeah, about 1/3 of the way. I have to read a few pages every night and go through it with my highlighter. So I don't try to overload my brain because my brain can't handle a lot of capacity. All right, HVACshop.gmail.com. All right, let's see if we popped up yet. Oh, okay, we're popping up. That's right. That's right. Bergman's coming back and maybe Bimco. So I hope Bimco can think of something interesting to say. I know that's going to be putting the pressure on him. He's like, what am I going to say? I've only been in the field for 1 year. Or whatever it is. I know it's 5 years. I'm just kidding. All right, keep commenting, guys. Keep chatting because we're going to pick a winner for the hat and shirt based on the chat. We're going to use Nightbot, and we have so far 5 eligible users. But if you keep chatting, you're going to pop up there. Frylock says, what the heck do I talk about? Frylock, we can come up with that, man. Okay, you already have a cool microphone. You're playing Call of Duty with it all the time. I know you're talking to your squad. You're going to flank somebody or whatever. But we can figure it out. It'll be all right. NorCal is going to be good. Yeah, chat. Just chat it up, guys. Keep chatting. We're going to pick a winner here in a second. There's, I put my guests into like 2 categories, and I hope this is correct to say, and it shouldn't be offensive, I don't think. When you start a sentence like that, it's like, all right, it's going to be offensive. It's not. It's either going to be field guys or these teacher guys. That's 2 groups, teacher guys, field guys, and both of them have a whole lot of stuff to give back as far as one of these events. And the teacher guys, the advantage they have is a lot of them are already familiar with doing this. So sometimes they seem like they're more at ease. And field guys come in here and they have a whole lot of information and some like salt of the earth information is what I call it. From working on certain machines, they understand how the machine works once it's been installed, which is a huge advantage as well. But the disadvantage is a lot of times the field guys, you know what? They're not used to being on the camera and doing the show. That's the one disadvantage, but that's not across the board. But I love talking to both of them. In fact, I had a whole podcast years ago called The Tradesman where we talked to field guys about just all sorts of stuff, not just HVAC, just what was happening in their life. It was a lot of fun. I try to duplicate that every now and then with some of the podcasts. Okay, we have 12 eligible users out there. We have, hey, I like that. Frylock says when he has a concern, he just calls Blue On, man. Blue On's got that wonderful commercial with all the cursing in it. Okay, a hat and a shirt. We have 12 eligible users. Let's pick ourselves a winner. All right. If you already have a hat or a shirt, when you email me, let me know that you already have one of those or both of those, and I'll substitute something else and make it a surprise. Also, if you win, make sure to put your shirt size and your address when you email me at hvacshoptalk@gmail.com. And Bob Reddington, email me your address because you already won something. Here we go. Our winner is 5, 4, 3, 2, 1. Lionel Stockstell II. You have been victorious. Lionel. Like the trains? I love trains. All right. Lionel. Very nice. Very nice. Congratulations. You won yourself a hat and a shirt. You probably don't have one because I've never seen your name before. And that's a good thing. I'm glad you're watching the show. It's a whole lot of fun. It's a whole lot of fun. Good, Bob Reddington. Yep, you won, Lionel. Fantastic. Make sure that you email me, okay? I want to take a second and thank Frylock, too, not just add to the pressure that he's already under having to be on the show eventually, but because he was the channel's very first member, and you can see his name right there. There's Bimco. You see him in the chat. He's got a little sign beside his name where he's a member now. That's awesome. That really helps out a whole lot because no, this is my job. I like to bring guys on and talk to them to kind of help you guys learn about the trade and become better tradesmen. And support like that is really the deciding factor for being able to do the giveaway stuff and just keep on doing it. And I really appreciate that. So thank you, Bimco. Bimco is also a supporter on Subscribestar. We have, I think, 12 or 13 Subscribestar supporters over there. So it makes a huge difference. You don't even know. So I just want to thank you for doing that. I really, really do appreciate it. It's awesome. If you need me, hvacshoptalk@gmail.com, like I said already. We're going to be back, or I'll be back tomorrow night on a different channel to do our Bible study. That's completely up to you guys. That's Men with Issues. If you want that information, I'll be happy to send it to you. Just email me at hvacshoptalk@gmail.com. I can hook you up with that. Frylock, if you're buying your way into stardom by being a member, okay. No, I'm just kidding. He's not. He's a good dude, and it's a lot of fun having him. I think it's gonna be a lot of fun having him on the show because he's already been on Skill Trade Up a bunch of times. We're gonna have a good time. No pressure on it. It's gonna be great. All right. So we'll be back next week with our other guests that I mentioned. I'll be back tomorrow for the Men with Issues show, Friday nights, 8 p.m. Eastern Standard Time. And guys, I'm gonna get out of here. I'm gonna go have a good time. Maybe turn this into a podcast and set it up for next week, or maybe I'll go watch. We're watching a Bible series, like the whole Bible. It came out like 20 years ago, and it has like 10 different stories. It's pretty good. So we might go watch that, have some microwave popcorn, and I'll see you guys on the next one.